Hello everyone, David Twyble here. A few days ago I posted a set of questions on my YouTube channel and on my LinkedIn page that have to do with aircraft energy management. And there are 8 questions, and I didn't give any answers, but a subscriber asked me to give the answers, so I figured I'd make a video here and discuss the answers with you. So let's jump right in. Question number 1. What are the 4 forces of flight? Well, if you're a pilot, you should know the answers to this question. Maybe you're not a pilot, or maybe you're a little rusty. And the 4 forces of flight are lift, thrust, weight, and drag. Now, of course, that's the easiest question, so let's ramp up the difficulty just a little bit here because it's going to get more interesting. Question number 2, what are the 3 kinds of aircraft energy? Now, there are lots of different kinds of energy in regards to airplanes, but here we're specifically talking about aircraft energy management and maneuvering. So we're going to generalize to 3 different kinds of energy, and they are potential energy in our altitude, kinetic energy in our airspeed, and potential energy in our fuel, or chemical potential energy. And those are the 3 kinds of energy we have to work with. And basically what an airplane does is convert chemical potential energy in the fuel into altitude and airspeed, which we can then trade back and forth and use along with more chemical energy. We'll talk more about that in future videos. Question number 3, what are the 2 kinds of drag? Which one increases with G loading and why? Well, the 2 kinds of drag are parasite drag and induced drag. And induced drag is the kind of drag that increases with G loading. And it increases with G loading because induced drag increases with lift. And so when you're pulling G's, you're pulling more lift on the wing, and so your induced drag is larger. And that influences several questions down the road and other issues regarding energy management. And we'll get into more of that in the future and more of an explanation of exactly why induced drag increases with G loading. It's fascinating, and most of all, it gets into wingtip vortices and exactly how those work. So we'll talk about that another time. Can each kind of energy be fully exchanged for another? That's meaning, can I turn fuel potential energy into altitude and airspeed, and vice versa across all 3 into any of those? And the answer to that is specifically no. Now, maybe from your physics class, you've done problems where you trade one form of energy back for another, and you end up with the same amount that you started with. And that is true in some very narrow circumstances, but in airplanes, we deal with aerodynamic drag. And because of drag is always siphoning off energy. And so we can never fully exchange one form of energy for another. We're going to have to pay a drag penalty. There are other penalties, but drag is the biggest one that we have to deal with in terms of energy management. Question number 5, with power at idle, at what airspeed and condition does the airplane lose energy the slowest? Well, that's a very interesting question because the way it's written has 2 answers, and either answer is correct. The first one that powered pilots would be most familiar with is what we call best glide speed, or VG. And best glide speed is the speed at which the airplane loses the least amount of energy over a given distance, no wind. Things change when you add wind to the problem, which we'll talk about another time. But that's one answer. The other answer is what we call minimum sink speed, or VMS, in the glider world. And VMS is where the airplane is descending through time the slowest. So best glide speed, you get the farthest down range, and minimum sink speed, you reach the ground in the slowest amount of time. And there's a distinct difference between those 2 speeds, and there are reasons why you would use one or the other, and we'll talk about that another time. In a propeller-driven airplane, how does thrust change with airspeed? Well, we're specifically talking about constant pitch prop airplanes here, and in a constant pitch prop airplane, thrust decreases with airspeed. I know that sounds hard to believe because that means that thrust is greatest when you're standing still, and that is true. And thrust is the least when you're going fastest, and that is also true. And that does make some changes in how the airplane feels compared to other airplanes, say versus a jet or a glider. That does have an effect on how the airplane handles and how it flies. And it's a fascinating difference. And there's a couple other ways to look at the problem, but that is the answer for that one. In level cruise, an engine failure occurs. Which is more energy efficient? Climbing while slowing to best glide speed, remaining level while slowing to best glide speed, and descending while slowing to best glide speed? And why? That's an really interesting problem because the answer is not very intuitive, and the correct answer is remaining level while slowing to best glide speed. And you might think that's kind of strange. Wouldn't you want to trade airspeed for altitude? And you can certainly do that. That is possible. But that does not maximize your energy in a situation like that, because it's a very energy intensive, or it's a very drag intensive process, to climb an airplane, because you have to pull G loading. That gets back to the previous question, even if it's a small amount, which increases your drag, which penalizes you for trying to climb and slow down. And descending makes no sense because you're burning drag faster than you need to. So the correct answer from a purely energy standpoint is to slow down level, then go down at best glide speed. And then the last question, a glider starts at 3,000 feet and 90 knots in level flight. The pilot pitches up and climbs to 3,200 feet. The moment they reach this altitude, the airspeed is 40 knots. They then descend back to 3,000 feet. Will the final airspeed be greater than, equal to, or less than 90 knots, and why? Now this gets back to the previous question about can energy forms be traded back and forth without a penalty? And as we said in that, the answer is distinctly no. You cannot trade energy without paying a penalty. And so if you're flying in a glider at an altitude and you climb 200 feet and you find yourself at 40 knots and you then pitch back over and level back off at 3,000 feet, you will be slower than 90 knots because you were paying a drag penalty through that whole maneuver. So you would actually have to go lower than 3,000 feet to get back to 90 knots. So as the old saying goes, there's no free lunch. So I hope you found the answers to these questions interesting. I will certainly post more questions in the future, and I look forward to discussing more of these aerodynamics and performance topics more in the future. Until then, fly safe.